Good afternoon. My name is Amir, and I'm doing PhD at University of Stavanger in Norway. So I'm working about at building a machine learning model for the optimization of the trip-in operation in the drilling and well construction operation. So this uh, paper is about we implemented the GMDH group method data handling technique to extract the mathematical model from the drilling data. So a little bit description about the drilling data. When we do the drilling operation, they collect they collect a lot of downhole data and from the surface data. So these data are measured from the different type of sensors, and it can be divided into two types of information, like the surface information and from the downhole information. In the surface information is consists of the rotation of the rotation of the motor, the flow which they pump in the fluid in the well is the pump rate, and then they have this speed at which they move down the pipe in the hole, and they applied some weight on the bit, that is also from the surface, and this the resultant torque which we produce from the RPM and the rotation is is also part of the surface data. Then we have the downhole type data, which is consist of the downhole information from the like the geological information and the fluid information and the about the drilling mechanics and all those type of information. And all these data are coming from different type of sensors, and these sensors can be like pressure sensor, temperature sensor, geological sensors, and so on. So we collected about 550,000 data set from one of the drilling operation in the North Sea, and then we collected the data and then we processed the data, because there are a lot of information which is not correct information. So we spend a lot of time on to do the data processing. There are a lot of non-values. We have to take those non-values. There are a lot of minus 999.25 values. That means the sensor is not measuring, and those we have uh, clean and we have removed. There are a lot of outliers, and there of course there are a lot of missing values also. And then there is a challenge that the frequency of the sensor is also different from each other. The surface sensor has a 5 second frequency, and the downhole sensors, some of them have 2 second and some of have 2.56 second. So there are a lot of challenge to integrate those data set. So we clean the data set, and we made sure that the quality and the consistency of the data set. We handle the missing values, outliers, and the data inconsistencies through techniques like data imputation and outliers detections. And first of all, we have to visualize the data set, because it's like a CSV files or Excel files, so we don't know what type of information is. So we decided, okay, we shall have a good visualization technique so we can visualize the data set and different parameters. So here is a illustration of the few features which we have from the main data set. And here we have implemented this bath plot to remove the outliers and yeah, clean the data set. This took a lot of our time to do the data processing. And then we last year we developed some machine learning algorithm like LSTM and XGBoost to predict the downhole pressure. That is our target. But we realize that we don't know what the LSTM and the machine learning algorithm is doing. So we need to find a method which can help us to extract the mathematical model from this information which we are receiving. So for this technique, for this purposes, we have used group method data handling is GMDH. It was originated by Professor Alexei, one of the Russian professor, and is a self-organizing modeling technique which use group of models like polynomials to construct a more accurate and robust model. The GMDH algorithm is multi-layered structure and can be described by Kolmogorov Gabor polynomial. And here is the polynomial like the target and then the coefficient plus coefficient time parameter 1 plus so on and coefficient time of first parameter times second parameter plus so on. Because in our data set there are about 29 different parameters which we can use as an input, and we have a one target, the downhole pressure to predict. So we have the input variables are described by the vector x, y, and so on, x1, x2, and so on up to xn, and slot and sole output is one variable which is our y, and this is representing the weights of the matrix or the coefficient of the vectors. Hence, GMDH is multiple input but is a single output system. So the system, if we have m input variables, one output variables, and then we can build this matrix, the input and the output matrix as we have the input variables, and then we have one target variables. And focusing on only two input variable at a time, the system equation becomes like this way. If we choose only two variables as input and one as output, then the system will become, the result will become like this way. And from this, we generated the regression formulation by taking the two variables. So we can simply do the regression technique and we can get the target y. So we didn't develop the software, but we updated one of the existing software they have developed for some other purposes, but then we updated with our own information. GMDH all software developed to extract mathematical model from the drilling data for the prediction of downhole equivalent circulated mud density, which is this is coming from the annular pressure of the wellbore. The primary goal to keep the ACD as output variable and try some other variables as input variables. So there are we can use a lot of other feature as input, like how fast the downhole velocity is, the pipe velocity in the hole, how fast we are rotating the strain from the surface, how much fluid we are pumping in the hole, like the fluid in and the fluid out, and this fluid are like the oil base or the is non-Newtonian type fluid, so we have to define the characteristic of the fluid also. So we did that, and we implemented this in the MATLAB. We added the input function for the drilling process and data processes and preparation, and we develop the graphical user interface. So for the user, it can be easy to put the input variables. And then we created the output function for the printing the results. So here is a experiment as an example that uh, in this experiment from the 29 input variables we choose randomly three variables like the bit position where the position of the bit is in the hole and the velocity of the pipe in the hole and the bit true vertical depth how much is far in the vertical with the with reference to the seabed and we managed to extract the mathematical equation which is this one on the base of these three input variables. In total, we performed 29 variables, 29 experiments, and with each experiment, we extracted one of the equations by implementing the different input combinations. And we have set up now in the lab experimental setup. We have built a rig, and then we are going to test these equations, how this will behave, how these equations are close to the experimental data set. The algorithm selects only two input variables and neglect the rest on the basis of best MSE. And that is the main shortcoming of this model. The other shortcoming is that it considers that the information is polynomial based, but is not necessarily that the information is polynomial based. It can be some other type of function because it's a dynamic system. So our aim is to extract the exact representation of this information of the dynamic system. In some cases, the algorithm never converge. So we found out that in some of the experiment, the system was not able to converge. It might be there are some non-values, but uh, we didn't find out if there was any non-values, but still the system never converge. So here are the examples of the some of the experiment number 2 and experiment number 3. Concluding remarks are that there are a lot of mathematical model available in the market for the prediction of downhole at the moment. And from that prediction of the downhole pressure, they can calculate the ECD value. But these models are very conservative and they are based on the lab experiments, not from the actual, uh, they haven't been tested on the actual environment. We realize that there is a lot of information now with the emergence of high-speed telemetry system, which can transmit the data from the downhole to the surface with 57,000 bits per second. And we propose that it's possible to use this new information to upgrade the existing models. And that's what the background is. We implemented the GMDH on the field data acquired from the drilling and tripping operation via the high-speed telemetry system from one of the Norwegian continental shelf field. Abstracted the mathematical model from the drilling field data to predict the equivalent circulating mud density. The prediction of the ECD by implementing GMDH are satisfactory, but we have not tested this model yet with the experiment. So that what we are gonna do now. Yes, thank you very much.
Questions?